At the age of about 5 or less, the typical child in an educated Western culture makes a cognitive leap that took humankind many thousands of years to achieve. The child acquires the concept of a number. He or she comes to realize that there is something common to a collection of, say, 5 apples, or 5 oranges, 5 children, 5 cookies, or 5 fingers, and so on. That common something, fiveness, is somehow captured or encapsulated by the number 5, an abstract entity that the child will never see, hear, feel, smell, or taste, but will have a definite existence for the rest of his or her life. Indeed, such is the role numbers play in everyday life that, for most people, the ordinary counting numbers, 1, 2, 3, 4, 5, etc., are more real, more concrete, and certainly more familiar than, say, Mount Everest or the Taj Mahal. The conceptual creation of the counting numbers, or natural numbers, marks the final step in the process of recognizing the patterns of members of a collection. This pattern is completely abstract, indeed so abstract that it is virtually impossible to talk about it except in terms of the abstract numbers themselves. Try explaining what it is meant by a collection of 25 objects without referring to the number 25. The acceptance of abstraction does not come easily to the human mind. Given the choice, people prefer concrete over abstract. Abstraction seems not to be something we are born with, but something we acquire, often with great difficulty, as part of our intellectual development. It is for this reason that numbers have kept us busy for thousands of years. Ancient Greece, the age of abstraction. An early adherent to the concept of mathematical proof was the Greek scholar Pythagoras. The Pythagorean theorem relates the length of the hypotenuse of a right-angled triangle to the lengths of the other two sides. A geometric proof of the Pythagorean theorem relates the areas of squares of figures drawn along the sides. The Pythagorean theorem also reveals things like irrational lengths. Proofs of such numbers created such a stir in the ancient world. Now, between the times of Pythagoras and Euclid, ancient Greeks observed and advanced mathematics with the works of Socrates, Plato, Aristotle, and Eudoxus. And it was at the Athens Academy, founded by Plato, that the theory of proportions was developed. An understanding of similarity is born. While working in the new intellectual center of Alexandria sometime around 330 BC, Euclid produced his mammoth 13-volume collection work called The Elements, which stands as the basis for planar and solid geometry today. Euclid begins Book 7 with a list of some 22 basic definitions. Among them are the definitions for even and odd numbers, as well as the definition for a prime number, a number that can only be divided by itself and 1. Among some of the other things proven by Euclid, every natural number is either a prime, or else it can be expressed as a product of primes in a way that is unique apart from the order in which they are written. That particular result is known as the fundamental theorem of algebra. He also went on to prove that there is an infinite number of primes. And here's how he did it. Consider the composite number 328,152. When broken down into the product of its prime number components, we get 2 times 2 times 2 times 3 times 11 times 11 times 113. Or more compactly written, 2 cubed times 3 times 11 squared times 113. The prime factor decomposition of 328,152. This is a unique decomposition, and it belongs only to this number. Now, the idea behind Euclid's proof that there is an infinite number of prime numbers is to start off by first assuming that there is a finite number of prime numbers. So, we will start with our assumption. We will assume here a finite number of prime numbers, and we'll write them as a list. The first prime, the second prime, the third prime, all the way up to some nth prime. Now, what we want to show is that this list must always have more primes in it. That is, that you can always build a new prime out of this list. So the way that we're going to do this is we're going to construct the number n made up of, well, start with the product of all our primes and then add 1 to it. Now, none of the existing primes that we have will divide this new number n. So then we draw a conclusion. This number becomes either a new prime or a number that is divisible by some larger prime. So, in either case, the list of primes is extended. And this can be done infinitely many times. It's subtle. The number n, composed of the product of all our primes plus 1, we don't know whether that number is prime or not. In other words, whether it's prime or composite. If it is a prime number, then it is a new prime number, not already in our list. However, if it is a composite number, again not prime, then it is divisible by, well, some prime that is not on our list, a new prime. A prime that must be larger than all the primes on our list. So the list of primes is always extendable. Thus is an infinite set of prime numbers. Where do the prime numbers live? If we take a look at the placement of prime numbers amongst the list of natural numbers, at first glance along the number line, they appear to be very clustered together. And then as we move along through the number line, it looks like the number of prime numbers spreads out. The density of primes thins out. So at first glance, the pattern here is not really obvious. Although there are some patterns here, like the twin prime conjecture, one can notice that there are primes that are exactly 2 numbers apart from each other, but not everywhere. And the open problem is to find out if there's an infinite number of these. So what happens when we go out to infinity with this density of primes? Clearly, there's a pattern to the primes that most of them, except 2, are odd numbers. So the problem is finding a pattern for when those odd numbers are prime numbers. And here comes the prime counting function, indicated by pi of n. Having nothing to do with the constant pi, the prime counting function counts the number of primes less than or equal to a given value, n. And so it gives us a way of keeping track of how many primes up to a certain number there are. This is what number theorists use to get a handle on the pattern of primes. Many mathematicians have given approximations to this, and this leads to something called the prime number theorem. Many attempts over the years to find a pattern that generates all the prime numbers, such as the Mersenne primes, have been tried but failed to find all. And mathematician Chebyshev showed that between n and 2n there will always be a prime number. So some progress has been made. Let's take a look at how the prime counting function evolves. So we'll make a table of values counting how many primes up to or less than that given n value there are. So if we started with n equals 1, 1 is not a prime number, nor are there any prime numbers less than 1. So we would assign that a value of 0. 2 is a prime number, 3 is a prime number, 4 is not, 5 is, 6 is not, and so on. And so every time we hit a prime number, the number pi of n goes up by 1, steps up by 1. And this is a discrete function because we're using the natural numbers and no other numbers in between. So when we plot something like this, we're going to get a discrete graph of dots, which we can analyze and think about a continuous function that might actually approximate the pattern. So here, plotting the values from our table, we can see that every time we hit a prime, we step up 1. And so this looks like a step function where there's plateaus. And if we were to try to guess what kind of function might model this, at first glance it looks like maybe a natural log function would do the trick in the way that it grows. And in fact, that would be a correct assumption. So when we want to analyze how closely a function will approximate the actual data that we're getting, we will look at sometimes the ratio of some of these things, and that's where we're going to get this prime density function. In 1896, it was proven, the prime number theorem, that the number of primes less than n is approximately n divided by the natural log of n, which we can state as pi of n is approximately n over the natural log of n. Now Legendre as well as Gauss had an idea that this was true, but were unable to prove it. And later approximations using integral forms of the natural log gave better approximations. If we were to look at a chart that looks at the percent of error between the difference of our counting function and the approximation function, we can see that as n gets larger, the percent of error in calculating that value goes down significantly, and that if we were to approach infinity, that error would go to 0. Now, getting an approximation is nice, but it doesn't tell you exactly how prime numbers are built. For now, we're going to switch gears and consider a serious problem. Consider the infinite series, 3/10 plus 3/100 plus 3/1000 plus 3/10,000. If we order this vertically, this sum will add to 0.3333, etc., repeating infinitely. And you might recognize that this actually sums to the fraction 1/3. So we have an infinite series that actually adds up to something finite. This infinite series is also known as an infinite geometric series. And we say that this infinite geometric series, when it has a value, converges. This one converges to 1/3. Not all infinite series converge on a number. But if we want to think about how infinite series work, especially geometric infinite series, we rewrite this in its fractional form. And by pulling out a 3/10, we can see that inside here we have a sum of 3/10 times the sum of all powers of 1/10 from 0 to infinity. That is the perfect recipe right there for a geometric infinite series of the form x to the nth power from 0 to infinity, which converges to 1 over 1 minus x provided the absolute value of x is less than 1, and in our particular example, 1/10 is. And this is what we call a requirement for convergence. Any power series, which says one of these is considered a power series, has a radius of convergence, or a value or set of values in which the series will actually equal some number. So if we plug in here x equals 1/10 into this formula, we retrieve 1/3. Now, of course, one might ask, what happens if you just use this formula willy-nilly for a value of x that is not an absolute value less than 1? For instance, let's say x equals 2. So if we had an infinite series of powers of 2, 1 plus 2 plus 4 plus 8, etc., it wouldn't take much convincing to tell you that this would go to infinity, get bigger and bigger and bigger. In other words, it would diverge. So a divergent series cannot be evaluated. And it is not always clear when a series will converge. A long-standing math problem was to evaluate the sum of the reciprocals of all the natural numbers to power p, for p equals 1, 2, 3, and so on. In 1350, Niccolò Orsini had shown that S1, the infinite series of just the reciprocals of the natural numbers, 1 plus 1/2 plus 1/3 and so on, diverges, which is not entirely obvious. And here's how this proof works. If we want to show that the series of reciprocal natural numbers diverges, that is, will not equal any particular value, we begin by writing out a few terms of the series, 1 plus 1/2 plus 1/3, all the way out to 1/8. Then what he did was group the terms in the following way. Now within these groupings, he considered, what if I replace all of the fractions within these groupings with the lowest valued fraction in that group, in the following way. Then this new sum, s, in blue, would have to be less than the sum that we were trying to evaluate. And the sum in blue is actually 1 plus an infinite sum of 1/2. And it wasn't hard to show that this infinite sum of 1/2 would diverge. That is, go to infinity. And since the value of S1 was greater than S, that proves S1 also goes to infinity. An ingenious proof. Now, finding a value for S2 would pose a roadblock for many mathematicians for many years. It was known that this series did converge to approximately 1.644934, but it was an exact value that mathematicians were after, and it was Leonhard Euler that made his name for finding the value of pi squared over 6 for this series. And here's how he did it. Euler said, consider the function f of y is equal to sine of square root of y over square root of y. And this function can be represented as an infinite power series. And this infinite power series is because sine can also be given as an infinite power series. Now, Euler said, consider this set equal to 0 as an infinite degree polynomial equation. He then argued that the roots of this equation would have to be such where sine of the square root of y is equal to 0. And we're going to exclude y equals 0 as a root because this function is equal to 1 at y equals 0. Well, the limit is in any case. So now the roots would have to be where the square root of y is equal to multiples of pi, non-zero integer multiples of pi, which means that the roots for y would have to be pi squared, 4 pi squared, 9 pi squared, and so on. Now, polynomials of finite degree, with a finite number of roots, let's say n number of roots, will have the general form f of x is equal to an x to the nth power plus an minus 1 x to the n minus 1 power all the way down to 1, and this is set equal to 0. The coefficients are connected to the roots, and this can also be written in factored form as x minus r1, x minus r2, all the way down to x minus rn as a product. Euler's ingenious argument was to say that this function f of x has a product of 1 minus x over r1, 1 minus x over r2, etc. for this finite number of roots is essentially equivalent to the function we're talking about here, and it has the value of 1 when evaluated at 0. Now, he argued that if you multiplied this particular polynomial out, the a1 coefficient would have the form and the connection to the roots of this, the negative of the sum of the reciprocal of the roots. And since he knew that the coefficient of the last term, of the x term I should say, of the polynomial was negative 1 over 3 factorial, or negative 1/6, he was able to now put the roots into this formula and connect it to the value of the coefficient. And lo and behold, he was able to pull out pi squared over 6 as the sum of the reciprocal of the natural numbers squared. But not only did he find it for this, which would be later dubbed zeta of 2, he would go on to find all the even input values for the zeta function. The zeta function, zeta of p, is the infinite series from n starting at 1 to infinity of 1 over n to the p power. We've shown that the zeta function value at 1 diverges, and Euler found the even input values for the zeta function and noticed that they were all powers of pi multiplied by some rational coefficient. And what he did later would be to connect this function to the prime numbers. Euler speculated that the zeta function took on specific values that were multiples of powers of pi. When p was even, it was a rational coefficient in front of a power of pi. When p was odd, he speculated that n was proportional to the natural log of 2. Searching for zeta 3. Zeta of 3, the infinite series, starting from 1 to infinity, of 1 over n cubed, or 1 plus 1 over 2 cubed, plus 1 over 3 cubed, and so on, or 1 plus 1 over 8th, plus 1 27th, plus 1 64th, and so on, is convergent. It does have a numerical value. Calculating this numerical value doesn't really take much, but it was only until Roger Apiary proved that it was irrational. Yet, to this day, we don't know if it is or has an exact closed form value. This is the open problem that could very well break or crack the $1,000,000 problem. This open problem is key to solving the Riemann hypothesis. As we'll explore a little later, the Riemann hypothesis is the million-dollar problem. Now, Euler comes pretty close to calculating zeta 3. In 1744, Euler made the claim that pi minus t over 2 is equal to an infinite series involving sine. Sine of t plus sine of 2t over 2 plus sine of 3t over 3, etc. can be compactly written as the series sine nt over n. Now, Euler's genius was to first make this claim and show that this is true for all t values between 0 and 2 pi. Then he took the leap and integrated both sides of this equation from 0 to x. Now, the left-hand side isn't really that difficult to integrate. We get pi over 2x minus x squared over 4 equals. And on the right-hand side, we'll switch the limit, the integration symbol, and the summation symbol. And we can do that using the dominated convergence theorem. Then integrating the sine of nt is pretty straightforward. We get cosine nt over n. And we're going to integrate that between 0 and x, so we'll get a function of x. So on the left-hand side, we have some expression in terms of x, and on the right-hand side, we have an infinite series. Now, if we break that infinite series up, part of it is zeta 2, and we know what the value for zeta 2 is. The other part, a series involving cosine. Replacing zeta 2 with the value pi squared over 6, we can rearrange the terms in this expression to give us the infinite series of cosine nx over n squared is equal to 3x squared minus 6 pi x plus 2 pi squared all over 12. The next leap comes from taking another integral from 0 to u, on both sides of this equation. On the left-hand side, we can pull that summation outside of the integral, and we'll get the integral of cosine nx over n squared, and then we're going to integrate that from between 0 and u. On the right-hand side, we simply have some polynomial-type expression, and once we integrate both sides of this, we can then let u equal pi over 2, and this was Euler's insight. So on the left-hand side, we have an infinite series involving sine, and on the right-hand side, we have an expression involving a rational expression times pi cubed. Cleaning up this formula, we get an alternating series involving the odd natural number powered to the third power, summed up, and that equals pi cubed over 32. Now, although this was not zeta 3, it was close to zeta 3, and in fact later on Euler does come even closer by finding a sum of the reciprocals of the odd numbers cubed. And we have some sort of messy integral expression. So really, zeta 3 remains unsolved to this day. But Euler makes a very important connection, which really sets the stage for our million-dollar problem. And that is, Euler connects the zeta function to the prime numbers. So if we let zeta of z equal the infinite series of 1 over n to the z, Euler began by multiplying the zeta function by 1 over 2 to the z. And on the right-hand side, we get this infinite series as a result. Then, it was his insight to then take the original zeta function and subtract this series from it. And that would result in this series, 1 plus 1 over 3 to the z, plus 1 over 5 to the z, plus 1 over 7 to the z, etc. And then we get this expression to be written in the following way. And then we repeat the process by multiplying the next result by 1 over 3 to the z. And that gives us this series. As before, we'll take the original zeta function and subtract this result from it. And what Euler noticed is that if he continues this process, he's going to continue to get factors that involve prime numbers. And so the left-hand side, if continued almost indefinitely, would result in an infinite series, or rather here an infinite product, multiplied by the zeta function that would equal 1. And then taking all of that infinite product, which can be compactly used and written with the pi notation, we have the product, the infinite product of all the primes, 1 minus 1 over prime to the z power, then multiplied by the zeta function, can then be solved for the zeta function. And so Euler connected the zeta function, this infinite series, to a product, an infinite product, involving all prime numbers. Now, what sets the stage for the $1 million problem is Bernard Riemann. In 1859, Bernard Riemann extended the zeta function into the complex number plane, and in doing so, cracked open a Pandora's box. You see, he noticed that the zeros of the zeta function are exactly the harmonics that are to correct the prime density function approximations, and that every zero added to this is going to get us closer and closer to the actual function that predicts the prime numbers. So the Riemann hypothesis claims that all non-trivial zeros lie on something called the critical line. That is, a complex number whose real part is equal to 1/2, and his imaginary part is not equal to 0. This is the open $1 million problem, in which if you can prove that all zeros lie on this line, the Clay Institute of Mathematics will award you the prize. And it is the holy grail of number theory today. So where does that leave us for zeta 3? Well, zeta 3 provides us with an avenue, a path, towards possibly making another notch in the belt of the Riemann hypothesis. Here we'll explore some alternative forms of a solution, casting new spells with integrals. In order to be a superhero in mathematics, you have to stand out, you have to break new ground, you have to think differently, as Euler did with the use of his infinite series and infinite polynomial equations. For now, I'm going to show you a few things involved with zeta 3, a few integrals that might just whet your appetite a little to explore this problem a little further and perhaps maybe find a solution to the Riemann hypothesis through zeta 3. So if you'll allow me just one more journey, if you've joined me this far, I want to show you two integral representations of zeta 3 that, if you play around with them, might lead you to $1 million. Albert Einstein once said, "Imagination is more important than knowledge." And it's going to take some imagination and creativity if we're going to move this problem forward. You see, this problem's been around for over 100 years. And maybe you'll be the one that cracks the code of prime numbers. Alright, we're going to show that zeta 3 first equals the integral 1/2 the integral from 0 to infinity of x squared over e to the x minus 1. Now this integral, an indefinite integral, we start out by multiplying both top and bottom by the conjugate of the bottom. In a sense, the conjugate, e to the x plus 1. What that does is gives us a difference of two perfect squares in terms of e to the x in the denominator. Next, we're going to take a little journey by transforming this by multiplying both the top and the bottom by e to the negative 2x. And you might be asking, why are we doing this? Well, what we're doing is we're trying to extract a geometric series that is convergent out of the integrand. And so now our denominator of our integrand is 1 minus e to the negative 2x. Now just that part of it alone is where we're going to see the infinite geometric series that we spoke of earlier. Because 1 over 1 minus e to the negative 2x is a convergent infinite series, a power series, which we can write in this following way. And so that we can replace our integrand with something that is more easy to work with because we can absorb that e to the negative 2xn into our integrand. So first we'll write it out, and then we'll switch our summation and our integral symbols using the dominated convergence theorem. Carefully writing out and distributing. We get an integral that we can split up using linearity. And that summation will remain on the outside so that whatever we get from these integrals will then be part of the summation we have to then ultimately do, if we can do it, at the end of the day. And what we're ultimately trying to show is that we're going to get the summation that is equal to zeta 3. Now what I'm going to do is a little integration by parts, but I'm going to use the tabular method to do it here. So on the left I am going to calculate the derivatives of x squared, and on the right I'm going to calculate the integrals of e to the negative 2n plus 1 x. Now this is something you've probably seen on the YouTube channel Black Pen Red Pen. And I think this is a great method when your integrand is a polynomial times an e to a power of x. So here you alternate the signs as we go down, and we'll connect diagonally or connect diagonally to write out the terms of the integration by parts. So I'm just going to write out the results here. I'm not going to go into too much detail as to how this method works, this tabular integration by parts method. There are plenty of videos out there for you to explore on how this process works. But what you notice is that our second integral is pretty much the same form as the first integral that we have, so we can just apply what we know about the first integration by parts to the second part, and then we can clean things up by applying our limits from 0 to infinity. Now at x equals infinity, we notice that the exponential part here, because it has a negative exponent, will be equivalent to evaluating 1 over infinity, which goes to 0. And so evaluating an infinity will cancel all of those terms out to 0. So then we explore what happens at x equals 0. And using the fundamental theorem of calculus, we'll see that once we plug in x equals 0, we'll be left with an expression in terms of n, which ultimately then we will sum up. So f of infinity minus f of 0, that minus sign minus f at 0, the antiderivative of 0, means that we'll absorb the negative out of that problem and everything will be positive. And we get 2 times this sum, which now is part of our summation. So this is what we've proven so far. Now if we examine what that series is really concretely by writing out or expanding out all the terms, what we notice here is we get 2 multiplied by the infinite series of all the reciprocals of the natural numbers cubed. And, well, wouldn't you know it, that's zeta 3. And so, multiplying both sides by 1/2, we've officially shown that the integral from 0 to infinity of x squared over e to the x minus 1 dx is in fact zeta 3. Oh, and one more thing. Zeta 3 can also be represented by this triple integral from 0 to 1, or volume integral from 0 to 1 in all dimensions, of 1 over 1 minus xyz dx dy dz. Now, triple integrals can be done, in a sense, in a separation way, and we're going to use another geometric series to simplify the integrand here. So rewriting the integrand as the infinite series of x to the n, y to the n, z to the n, from n going from 0 to infinity, we can use the dominated convergence theorem again to pull the infinite series outside of the integration. And then we can start doing the integrals one at a time from 0 to 1, and here we'll start with x to the n dx from 0 to 1. That'll result here in 1 over n plus 1. So that's like a constant here in terms of our integration, and we can pull that outside. Next we'll attack the variable y. And again, it's pretty much the same deal here as x, only with the dummy variable y. So we'll get another factor of 1 over n plus 1 outside of our integral. And I think you know what's going to happen with this third integral. It will just absorb another constant of 1 over n plus 1. So we ultimately get our infinite series from n starting from 1 to infinity of 1 over n cubed, or zeta 3. Well, there it is. I hope you liked this video. Please hit that like, subscribe, and notification bell for more videos, and stay tuned for the next one. And good luck on your quest for cracking the $1 million problem of the Riemann hypothesis.